This is the ELEC 1510 Logic Design Lecture 3, Video 2 on Boolean Functions. This one is going to correspond to the textbook section 2.5. So let's quickly review truth tables. This was in the previous video as well. Truth tables contain all possible combinations of input values. So for the equation z equals x or y, we're going to write out all possible values that x and y, which are the inputs, can take, which are 0, 0, 0, 1, 1, 0, and 1, 1. And then based on those inputs, the values that z takes as the output. Same thing for z equals x and y. We've got the same set of inputs, the combination of all possible states that the inputs can take, and then the corresponding outputs for all of those inputs. So that's what truth tables look like. Now, Boolean functions can have lots of combinations of variables in them. There are three ways that we can represent the behavior of a Boolean function. We can either represent it as an equation. That would be something like z equals x and y. We can represent it as a truth table, so that would be x, y, z with 0, 0, 0, 1, 1, 0, 1, 1, and for z equals x and y, that's going to be 0, 0, 0, 1, or as a logic circuit. So this can also be translated into a logic circuit where we use an AND gate with the inputs x and y and the output z. So all of these are equivalent ways to represent Boolean functions. So let's look at a more complicated Boolean function, z equals x prime y. So this is where we are performing the AND of x prime and y. X prime, again, is the opposite of x. So that means that whenever x is 0, x prime is 1. And whenever x is 1, x prime is 0. So in the truth table, I can actually fill in as many intermediate variables as I want, and I've created a new space for a new input, x prime. And so in my new x prime column here, I'm going to just fill in 1, 1, 0, 0, the opposite of x. You don't have to do that, but it does at first make it more convenient for you to analyze the function. So now we know that for z equals, let's just use two arbitrary variables, a and b, z is going to be a 1 only if the two input variables are both 1. So I have to look at the two input variables, y and x prime, and look at where they're both 1, which is only here, and that is where the output is going to be a 1. For any of the other inputs, at least one of the input variables is a 0, and so the output is going to be a 0. So now let me erase all of that. And now we can look at our set of inputs, x and y, and our output, z, and see that, well, for these inputs, we have the input variables x and y, and for the function where we manipulate those in x prime and y, the output z looks like this. Now the way that we would draw that as a logic circuit is, well, we know that z is the output of an AND gate, and we have two inputs to that AND gate. One of them is y, and the other one is x prime. And so in order to get the negated version of a variable, we have to use an inverter. So we'll plug x into an inverter, and then plug that into the second input of the AND gate. So again, all of these are equivalent. So let's look at a more complicated equation now. Z equals x prime y or wx. Now eventually we're just going to quit using the or and So I'm just going to call this z equals x prime y plus wx, with the implication that the plus means or, and whenever we have two variables written next to each other, that means and. So I'm going to conveniently fill in a couple extra columns into my truth table for some of the intermediate variables, because this is basically a z equals a or b, where a is x prime y, so that would be this column, and b is wx, that's this column. So now if I can just figure out what those are equal to, then I can perform the z equals a or b with these two columns and get the answer. So first I want to write down x prime, and I have all possible values that the inputs can take here, x, y, and w. You'll see now that there are 8 rows because 3 variables leads to 8 possible combinations, 0, 0, 0, all the way through 1, 1, 1. So x prime, again, is just the opposite of x. So whenever x is 0, x prime is 1. So we have 4 ones and then 4 zeros. Now x prime y here is going to be a 1 whenever both x prime and y are 1. So that would be here, that would be here, and that's it. So there are only 2 places where both x prime and y are 1. So I'll fill that in. And now xw here is going to be a 1 whenever both x and w are 1. So that only happens here, and the rest of these are zeros. Now z is equal to x prime y plus wx in Boolean terms, or wx, which means that z is going to be a 1 whenever either one of these, x prime y or wx, is a 1. So I can look at the truth table for these 2 rows here and just look for whenever either one of those is a 1. So here one of them is a 1, here one of them is 1, here and here. And then I'll fill in the rest being zeros. And so now, based on my inputs, x, y, and w, I know what my outputs are in terms of z. And again, I filled in all of these intermediate values just to help. You don't have to do that, but it does help quite a bit. So now let's draw what the logic circuit for this Boolean function would look like. We know that this is basically, again, a z equals a or b, where a is x prime y and b is wx. So z is going to be the output of an OR gate. Now, the term a here is x prime y, so that has to be the output of an AND gate, where one of the inputs is x with an inverter, and one of the inputs is y, and then the other term for this line is wx. So I'll write a w and an x. And so there's the logic circuit that represents that function. And this logic circuit is equivalent to the equation, and it's equivalent to the truth table that we drew on the previous slide.